How's that? Oh my gosh, I can hear myself. Oh, wow. So hi, I'm Dave Mcallister. I work for Nginx. Nginx is owned by F5, but I don't talk about them very much. I work for Nginx. I'm an open source geek. I started with open source, what is now called open source, in 1992. Got involved in Linux in '94 and have been open source since then. However, today, I will be mentioning Nginx a couple of times, but this is really a kickback and have something very different. And this is about the statistics behind the alerting system that we all depend on when we run our systems. So let's start off with the fairly simple, what's the difference between a mean, a median, and a mode? How many people here think they know what a mean is? Okay, more than 20%, sorry. Most of y'all probably have some idea. How about a median? Okay. How about a mode? Okay. Okay, for everybody who raised their hands 3 times, the extra credit question is, what's the 9th data kind number? And I'll give you the answer at the end of the talk. So statistics and monitoring is a numbers game. Metrics are the numbers that represent our best view of what's going on inside of our systems and inside of our applications. Generally, they're time-stamped. Generally, they're key-valued pairs. However, for data to be useful, it needs to be aggregated, analyzed, and usually visualized so we can see what's going on. Sitting there with a tail minus F and looking at a stream of numbers coming from your system is probably meaningless. But looking at this data as it goes forward. The picture over here is sped up, but this is a red monitoring system, rate, error, duration, based on open telemetry tracing. Showing the system, and you can see over a 10-second period what's happening on a second-by-second basis, and you can see how error rates are going up and down. And this gives us an idea of what we're looking at. Numbers lie. So keep that in mind. My other talk is about how to lie with statistics, but numbers lie. And so Nginx, of course, has monitoring. We have lots of different things in here. We're a reverse proxy. We're a web server. We're a mail server. We kind of can do any of those different pieces here. But again, monitoring is essential. And the thing is that monitoring is actually really essential for you when you know what you want to monitor. Your specific goals matter. The problem is that we blindly trust computers. We blindly trust that what we're seeing on the screen is meaningful. So I started off by talking about those other pieces. And what we are really concerned about is not usually the general behavior, but the outlier behavior. So how do you deal with outliers and the spike activities? And spikes can go down and spikes can go up here. How do you get a representative value when things build on top of each other? And then how do you, for instance, get a value that represents change over time? These are all different approaches to how we deal with our statistical lives. And honestly, do you actually know what it's telling you? I have to tell you a quick side story here. I got asked to do this for a large conference once, but they said you had to include AI. And so I said, fine. And I went up and I asked one of the AI systems to solve a very standard problem, exponential distributions. We'll cover those. It came back and my answers didn't agree with it. And of course, I blindly accepted that the computer was right and I was wrong. Turned out that when I did it again, my answer still matched. And so then I went and I asked a different AI system who came out with a 3rd answer, a 4th answer, a 5th answer, and so forth. So if you don't know what is actually being generated, how do you know whether the answer is right or not? So anyway, mean, median, and mode. By the way, it's a trick question. So keep in mind when I get to that, but mean, median, and mode is a trick question for that. So here's a series of data. A mean is a measure of central tendency. And in fact, all of these items are central tendencies, where something is happening in the most common element here. So the mean is the central tendency of those different pieces. The median is the middle item of a sorted list. And the mode is the most common item in that list. So it's very simple, very straightforward. So given that data set, the mean is 5.444. Median 6, mode is 1. Or is it? The mean is 4.130, 2.791, and all 3 of those answers are correct. The reason behind that is that there's more than one kind of mean. There's arithmetic mean, which is probably what most of y'all thought of when I asked that question. Add the numbers together, divide them by the number of items, gives you a central tendency number. So that arithmetic mean is very straightforward. Harmonic mean, another one of the classic means, is multiply the numbers together and take the nth root. So if you multiply 100 numbers together, you take the 100th root. That's the geometric. And the harmonic, sorry, that's geometric. Harmonic is take the reciprocal of all the numbers, add them together, and then divide it into the number of items. Now, they each have values, and they each are used in different cases. And so, start with arithmetic, the most common. This is the one everybody does. It's the central point in that wonderful bell curve, that normal distribution that we use, Gaussian curve, bell curve. For this, it is not usually the 50% point. This is something everybody always ignores immediately. Unless your mean point is 0 and your standard distribution is 1, it's not the central point. So if you think of the number coming out from mean being the middle, nope, not going to happen for that. The time series, we almost constantly are tracking new data. And so we now have time series data, and we actually only look at part of that. And so our structure moves with us as we're moving across. So load balancing model, add the 3 together, divide by that, we end up with 200 requests per second. And this works really well in a single load balancer model with 3 systems who have pretty much basically the same power and capabilities. Geometric allows me to compare different things together. So now I can look at request and request time and get a central tendency of those 2 things. This is where I multiply things together and where it becomes a very straightforward point. In DevOps, number of deploys per unit of time, how often I deploy things, whether it's an MTTR method, throughput, how fast things are going through the system becomes really point. This also allows me to build. So if I want to do an improvement on my sprints and I see a reduction in my sprint 1, 2, 3, and 4, as the list shows you, then all of a sudden I'm back to the point where it says they've got to build on each other. So what is my central tendency point for that build? You can't just add them together and divide it. The number is not correct. And so you do this from a geometric viewpoint, and you will get that your geometric mean of 0.937, or about a 6.3% increased improvement of time. And then harmonic. This is the divide by the reciprocals, which divides into that number and then gives us a result. Those 3 numbers I showed you of the very first chart are the arithmetic, the geometric, and the harmonic. Arithmetic will always give you the highest result, always. And harmonic will always give you the lowest result. And so you can actually play games with your means because, very honestly, nobody gets this, by giving them a mean that matches what your needs are. And so in DevOps, we look at this a lot from a range of performance. Are things staying within a range of behavior? Centralized tendency again. It's incredibly useful. Harmonic is incredibly useful for looking at outliers because, once again, it's the smallest set of differences, and therefore, if it's an outlier space and you can compare the 2, you get an outlier viewpoint. So harmonic is pretty straightforward. So I always like this one. This is how you can lie with means. And sorry, my data is US for this. Average income is about $59,384. Average household is 2.63 people. Therefore, the average household income is $156,179. No, it's not. It actually is roughly $105,000. And this is how means can be used to mislead you. If you are using a mean and then multiplying it back out, you've changed the rules of the game. And so keep that in mind. And by the way, given those data, if you want to earn $1 million, you just need 14.8 kids. So During one of these talks, somebody came up and says, well, what I do is I take latency and throughput and multiply them together, and then I compare that data. And this is the data from one of their charts for this. And the suggested metric will show you that if you look up here, my suggested metric comes out to 10,000 in each of these cases. But my mean is drastically different in all three categories. In the GM category, the geometric, because that's what you're actually building. He's building a geometric mean out of this. And it might be useful, but it doesn't weight the right things. It's not actually telling me anything really useful. The three charts down the bottom, again, are the metric categories. And you can see they follow the same pathway. That's to be expected. They actually centralize at 1 point or 2 points inside of this. But it's something that doesn't necessarily make sense. OK, really cool. I just introduced you to geometric and harmonic. Why don't we use them? Well, there's this little thing called, this nasty thing called a zero. And zero can't be used in either geometric or harmonic. Remember, harmonic is taking the reciprocal. 1 divided by 0 is meaningless. Geometric multiplies the numbers. However many numbers you multiply together times 0 is 0. The square root of 0 is undefined once again. And so you cannot use them if you have a 0. So that's why we don't use them. But in certain cases, they're still very, very powerful. Request timing is incredibly useful in these. OK, median. This is actually the chart that started the entire talk that got put together for this. The median turns out to be amazingly underutilized. And it has some really interesting points. First of all, the median is always the 50% point. Always. By definition, it's the middle point of your sorted list. It has to be the middle point for here. And that gives us some values. If we know the median, we actually always know exactly where center is. And what happens, though, if you are using a historical anomaly or a sudden change model inside of this, and you're using the mean can change drastically. In this case, it's I think, 30 days worth of data, or something like that. I can't read my own set. A little bit more than that for this. And we had a spike occur. And the spike is substantially larger than what our mean was. And because of that, our mean, our arithmetic mean, jumped up. It does not return immediately to the next point. It slopes down. As the numbers return to normal, it slows down. So if you're looking at sudden change, you're now looking at sudden change against something that's no longer valid. Hopefully you fix the problem that caused the spike. Whereas the median changed by 1 number, which is already in the central tendency line. So it's close to the middle point as it is. And so, again, using mean is useful for the central tendency, but using median is best for using for alerts. This is actually really something that bugs the heck out of me, because when I go around and people talk to me about how they're using means, it's not the best approach. And by the way, this is what it looks like with a harmonic distribution. It follows pretty much the same trail. Harmonics do not respond to single number changes. But again, you can't use harmonics with zeros, and so it has to be careful. So if you're using this model, this median model, you're actually using a 50% point. You're staying at the 50% point. If you're using P95, percentage 95, it's out of range, 90-95, you're already using a percentage value. Congrats. I won't yell at you for not using the median, but keep in mind that you're using a structure that does not react to sudden changes, while at the same point giving you the ability to control where your data lives. So, sidetrack here. This is called the measure of variability. If you don't know, if I look at you and say, 63, the mean is 63, it doesn't tell you a lot. Am I telling you this with 2 numbers, 64 and 62? Am I telling you this with 10,000 numbers? Are my numbers widespread, or are they not? So knowing how they vary becomes really important. And there's this thing called an interquartile range, which basically takes that ordered list and says, here's the first quarter, here's the second quarter, here's the third quarter. And the reason that we are most interested in interquartile, standard deviation is what everybody lives with. We'll talk a little, I think, about that. But interquartile has a couple of advantages. So let's see, where am I? Okay. So this is an example. Death Valley, one of the hottest spots on Earth, the mean temperature is 61 degrees or 16.1 Celsius. Death Valley has a range from 40 Celsius to 15 Celsius. Either of those two ends, you don't want to live in there. Well, 15 is not bad. But at 40, you don't probably want to do there. But in the middle, 16 sounds pretty comfortable. So you have to know what your range is to understand what your behavior is. And again, two identical data sets, more or less. Sample A, sample B, their means are exactly the same. Their deviations are drastic. And so how they change is really important for how your data is spread. And the data spread becomes really important because the more data you have, the narrower your deviation spread should be. So if you have one person, you can have a lot of range. If you have 50 people, you have a different range. And so knowing, again, your data set makes it really important to drive that. Talked about the interquartile. This is an outlier formula. It's visualized here. The outside edges are good candidates for outlier behavior. And in fact, there is this rule of thumb. There is no math theory behind this. It's just something that happens to work that says, if you take those two pieces from the Q1, Q3, take the length of that range, multiply it times 1.5, and add it on, subtract it from each of those ends. If it's outside those 2 points, so those red points on this line, it's an outlier. And it's almost perfect a point of saying it's an outlier. It may not be every outlier because you could have outliers that are inside that range. If it's outside that point, it's probably an outlier. And so you need to consider what an outlier means to your structure. So, mode. Mode is one of those underutilized things, the most common recurring set. Usually we see it as histograms for this. And we don't use it a lot, or at least we don't use it a lot in our DevOps work here. But we do look at it in log analysis. We look at it in user behavior. What are people commonly doing with the system? What is their common pathway through the system? So user interfaces and user behavior become a really important part of a mode environment here. It can also be used for security monitoring. Are you seeing common behaviors and then seeing outliers to common behaviors? It's not something that's easy to track from a pure metrics basis, but it's easy to track by a counting basis, which is what mode really is all about. And so we're going to get into the next sidetrack here. There's this thing called descriptive, and there's this thing called inferential. Descriptive statistics are using every piece of data. Inferential statistics are using a subset of the data to represent the data as a whole. I can't tell you what every person in the world thinks, but I can grab a subset of people and infer from that what their behavior is. So both of them get used to draw conclusions. However, descriptive, the conclusion is pretty precise. You don't have any of the data that can change around that. The other side can be really interesting. You can get biases creeping into it drastically for this. What this does in statistics is leads us to sampling. I've worked in open telemetry for a while. Between logs, metrics, and tracing, I have so much data that I can't handle it all. I can't visualize. I have one customer who does 43 terabytes of tracing data an hour. That's a lot of data. You cannot do this. So you have to look at sampling. But sampling has its own set of risks for here. What happens when we do this is that we sample things, and we can sample them in different ways. And the ways in which we sample affect how we get results. In OpenTelemetry, we hear head-based and tail-based, even though tail-based isn't really sampling. nonetheless, one says random pick, one says pick it on a set of criteria that I want to establish. I saw an error. I saw something that was an outlier space. And that makes us a set of data that is not necessarily purely representative. Here's an example. The first set up here is a sampled model. Literally forgot what my sampling model looks like. But as you can see, it doesn't look too bad. It's got 1, 2 problems that are showing up in here. Likewise, the latency distribution for that is working out that I've got a couple of things at 1 to 2 seconds. That's my 95th percentile. When I look at the entire set of data, I have problems appearing all over the place. I have lots of things that are appearing. This is not a random model. And I have traces going out to 29 to 40 seconds. And so depending on how I sample changes the way my data is presented to me. Changes the means, the outlier structures, all those different pieces. And it can make it really hard to do the forensic exercise to figure out what's causing that 29 to 40 seconds. According to Google's surveys every year, 3.7 seconds is known as walking away from a shopping cart online. 3.7 seconds. So if I've got something running 40 seconds and I'm expecting something under 1, I have a problem I need to look at. Now, the good news is metrics are seldom sampled. I have seen it, but not often. For that, traces get sampled a lot. And traces can lead to metrics. So hopefully you're looking at all the metrics we're tracing, not just some of them here. Mixed forensics can be a lack of direct correlation inside of here. It's a necessary evil. No one wants to store 43 terabytes of data per hour for any length of time. It's bloody expensive. And so we have to deal with this, but keep in mind that tracing changes the nature of the statistics you're looking at on the screen, the alerts that you're looking at. It can also exhibit bias. And bias can manage a lot of ways. Cognitive bias, but the one that's actually found most often when we're looking at these is what's called recency bias. There has not been a problem recently, therefore there will not be a problem. That is a falsehood. The fact that there has not been a problem recently doesn't change the impact that there could be a problem. It's like flipping a coin. You can get a heads or tails. You can flip 3 coins. What are the odds of getting 3 heads versus each coin being a head is very different. So keep in mind that looking at your data can have a recency bias. And keep in mind historically that things may be different. You may not have had a deployment in 3 months, and then you deploy 3 things in 3 weeks. Probably you're going to have a problem. And it's probably related to that. But that's secondary. There are lots of different distributions that can help inside of this. We talked about the normal one. That's our wonderful bell-shaped curve for this. Poisson, which lets me look at the occurrence of events. And so that becomes a request timing model that comes into play for that. Beta, which is A/B testing. Test 2 things, one against the other for that. Exponential, which is the time between asynchronous events. And we're going to talk about that one because that one's fun. Weibull, what's the odds of failure? Literally, you can actually figure out what the odds of failure are in a particular category. And then log normal, which is, interestingly enough, when your data, you take the log of it, it may become a normal curve. This data curve that you're seeing here, which starts high at the right and moves down, if you take the log of it, it actually becomes a normal bell curve. And so that's what those 2 things are. Slight sidetrack, standard deviation, because standard deviation plays a role in every one of these calculations. Standard deviation shows me my range, but at the same point in time, in a standard deviation in that normal curve, which is the only place standard deviations really make sense, it shows me what the ranges are. All my values in the first standard deviation, 1 to 1, should be about 68%, all the way out to 99.7 when I go far enough out at 3 distributions. And so standard deviation can tell me what my ranges are with some chances of also looking at the outlier behavior. Those 2 pieces together, again, give me the ability to say, there's a problem going on, and I need to take advantage of it. Okay, exponential. By the way, this is the one that I challenged all of the various AI tools with, and they all got it wrong. And I've checked my math more times than I care to think about. Okay, there is literally, once you've taken your data, there is one variable. This is like one of the easiest statistical equations you will ever see in your life. Everything else is a fixed value for that. So E, 1 over the mean, and then the equation is 1 over mean times E times 1 over the mean times the X, which is the single variable that you care about. And so it gives me a latency or a throughput, asynchronous events. This one I love dearly for that. And so you can see very quickly that I can come down with the exponential viewpoints and come out with what are the odds of a particular event occurring at a particular point in time. So my throughput probability density at 58, just 58 is 0.62. However, the cumulative, something happening within that time frame, is 58. And remember my discussion about median? It gives you a median. And so median can be used here to say, hey, something should have happened by now. I should have seen a request coming in. Why is my system not talking to the outside world, or why is the outside world not talking to me? And that becomes a really important aspect. You may stumble upon this on scale. Statistics are not your friend. Wrong. On scale, probability is not your friend. Statistics are history. Probability is trying to predict the future. So if the odds come out and say 1 out of 10,000, that's a probability structure. And by the way, probability can also be wrong. Coin flips are not 50-50. They're actually 51-49. It has to do with precession. People can flip a coin. Generally, the coin will make a specific number of rotations. It doesn't matter what coin you're using. Doesn't matter who's doing this. A blind flip comes out to 51-49. And kind of interesting structure. And the best way to do this is not show the person what's up on the face of the coin. And by the way, with practice, people can flip a coin and land on the same side every single time. So coin flips are an example of probability that we talk about all the time. Finishing up as much as I can, this is known as the Monty Hall problem. And this gets us into this concept called Bayesian, which every DevOps guy probably uses and doesn't know about it. You got 3 doors. Monty Hall problem says behind 2 of these doors are goats. Behind one of these doors is a new car. Pick the new car and you win the car. And you pick door number 1. Monty would look at you and go, let me open door number 2 for you. And behind door number 2 is a goat. Now Monty knows where everything is. Should you switch doors or stay with the same door? How many people would switch doors? How many people stay with the same door? Okay, everybody who raised their hands for switching, well done. Here's why. 3 doors, 1/3 probability on each door. 1 door is taken away, 1 door you pick, 2 doors left. 1 of those doors goes away. The probability doesn't change. The probability between those 2 doors changes. And so now your original door is 1/3, your other 2 doors is a 2/3 probability, so 1 of those doors now is a 2/3 probability. This got argued about for years, by the way, and it's massively still fought about today. This is called Bayesian theory, and basically what it says is if you get new data, you are allowed to change your mind. Keep that in mind. In my space, I constantly get new data. I constantly change what the underlying factor cause could be. There are lots of pitfalls inside of this, but correlation is a big one. And this is my favorite sneaky correlation. This is correlation of marriage to the sale of beer. And they are almost a perfect match. So does drinking cause marriage, or does marriage cause drinking? No, neither one. It's a confounding variable. Something else is causing these. In this particular case, it's population growth and aging. As we got more population, we got more people growing up, more people got married, more people drank beer. And that's a confounding variable. Correlations are sneaky. And by the way, correlations can go both ways. So you can have reverse correlations for this. And oh, by the way, I don't have the slide in here, but if you go look at it, you'll find that Internet Explorer caused murders. because as Internet Explorer use went down, the murder rate went down as well. So statistics are how we analyze our metrics. They are great aggregations. They reveal central tendencies for this. We usually use only a few things, but there's a wide world of other choices that we can make in here. And finally, the most effective debugging tool is still careful thought. Brian Kernighan said this in 1979. I think it's one of the best quotes I've ever seen, coupled by judiciously placed print statements. Metrics and their aggregations are giving you that information. And with that, that's the answer to what the 9th data kind number is. So if anybody got it right, let me know afterwards, because I certainly didn't. And statistics are history. History is written by the winners. So when somebody shows you statistics, be sure that you understand what you're reading. And with that, thank you very much, and I'll get off stage and let their next speaker get on board. Thanks.